welcome. Forces lesson 3. Forces lesson 3. Gravity, mass, weight. What do they mean? I have to make a confession, you lot. Okay, now the first lesson was basically everything you need to know for Key Stage 2, so if you're under 11, but we added some more details. The second lesson was pretty much all Key Stage 3 content, so between like 11 and 14 years old. This is actually all stuff that you will only learn really at Gcse, so 14 plus. But nature doesn't know that, does it? Nature doesn't know that bits of it are harder and bits of it are easier and that we're chopping it up. It's all there to learn, isn't it? So let's learn it. But if you start thinking, this is quite deep and dark and detailed, that's why. So, making no apologies. All right, so first of all, mass. Oh, I need to flip my screen, don't I? Right, mass. What is mass? We don't use the word mass very much. But you'll know what it's measured in. It's measured in kilograms. So like if you said a time, like you ran something in 10, you would probably say seconds. Time is measured in seconds. Distance is measured in meters. Mass is measured in kilograms. Or for physics, but you could say grams as well. You've probably heard of kilograms and grams. What is mass? Well, strictly speaking, mass is a measure of how difficult it is to get things moving, or how difficult it is to stop them. So me, a big thing, sitting on a sofa, it's harder, like if you were trying to pull me off the sofa, it would be more difficult for you to do that than it would be to pull like my 2-year-old off the sofa because she is very small, okay? So mass is a measure of how difficult things are to move. Something with more mass is harder to move than something with a small mass. And mass is the same wherever you are in the universe, all right? So imagine space. We'll talk about weight later, but most of you probably know that in space you're kind of weightless, like you're floating. Gravity isn't pulling you down anywhere. But if in space you put your hands on me and tried to push me through space, you'd still need as much force as you did before. Like I would still be harder to push than my little 2-year-old if you wanted to push her through space. I mean, don't, but we're talking hypothetically. If that's very confusing, you can think of mass as also being how much stuff is in you, like how much stuff are made of. Oh, I really like saying, how old is this from? So everything I'm going to say is for like 14 plus, but I'm hoping to explain it in a way that means that people who are much, much younger can understand. So just listen and see, you know. Yeah, you could think of mass as being how much stuff you're made of, or how much stuff a thing is made of, because that kind of works too. I'm made of more stuff than my 2-year-old. But strictly speaking, or if you really want to, you could just think of mass as being big or small. But strictly speaking, it's how easy or difficult things are to move. Okay, so that's mass, measured in kilograms, same everywhere in the universe. Right. Now we're going to talk about weight now. Let's talk about weight. I'm going to take quite a big run up. I'm going to show you this trick that I just showed you in my little box and show you how it works. Although a lot of you have got it already, haven't you? So I did this with my kids the other day. This is a shoebox that they decorated. I'll move the camera's flipped, it's a bit confusing. I'll move this person because they're not really doing anything. So it's just a piece of cotton sellotaped to the bottom of a shoebox, and inside this kite, some of you sussed, is a paperclip. Yeah, you can just see it actually, can't you? There you go. And on top is a very, very strong magnet. It's ludicrously strong. You couldn't do this with like a fridge magnet. But how good is that? Like look how far that is. Isn't that amazing? And look, I'll show you. Have you ever thought about this really with magnets? So you know, don't you, if you've held two magnets close to each other, you can feel them pulling on each other even before they start touching. What is going on? Like, how does that happen? What is happening there? So far, we've talked about things called contact forces. So a contact force, contact means touching. So a contact force would be a force that when you touch something, you apply the force, right? So we've been pushing balls and stuff and little Lego horses, haven't we? And seen that you touch something, it moves. That's a contact force. Magnetism is called a, guess what? Non-contact force. Because you don't have to, the paperclip doesn't have to be touching the magnet to feel the force. So what's happening? Well, it's not air. Magnetism doesn't involve air. Like, this would still happen in space where there is very little air and very little gravity and stuff. So yeah, you ever thought about that? What's in this space? Well, the answer is something called a magnetic field. Thanks, Myra. It is cool, isn't it? Yeah, exactly. Someone's saying the north and south are attracted to each other. So if you've ever seen like cartoons, sort of pictures of magnets or whatever, you might have seen, don't worry, we're not actually learning about magnets, doesn't matter if you don't know this, but you might have seen magnets with lines around them. Yeah, you ever seen that, like on the front of a science book or something? So obviously if you've ever seen a magnet, you know that those lines aren't actually there. But you often see magnets drawn like this, and what these lines are showing is the magnetic field around the magnet. It just means the bit where like metal things that are coming in experience the pull of the magnet. And we know, don't we, that if you held a paper clip there, you would feel a bit of a pull, but not as much as if you held it closer. So the closer you get to the magnet, the stronger the magnetic field is. And we also know that if it was a teeny tiny magnet, you wouldn't feel that much of a pull. But if it was a really big magnet, or really strong magnet, you'd feel more of a pull. So big magnets tend to have a stronger magnetic field, more of a pull. Little magnets, less of a pull. And the closer you get to them, the more you feel that strong pull as well. All right? But we're not talking about magnets today, are we? Well, it turns out gravity works in a very, very similar way. So everything that is made of stuff has what we call a gravitational field, right? Usually you don't feel it because most stuff is very small. Like, you have actually got a force of gravity, but it doesn't. You can't tell because you're so small. You haven't got many particles in you. You're not very massive. The Earth is really massive, so you can really feel its gravitational field. Just like the difference between a teeny tiny magnet that doesn't do anything and a massive magnet. The Earth is massive, so it's got a really strong gravitational field around it, okay? And instead of magnets, where metal stuff feels the magnetic field, with a gravitational field, anything made of stuff feels the gravitational field. So anything made of stuff that comes near the Earth, as we know, gets pulled towards the Earth, right? Are you with me so far? If the north are facing each other, then would they be repelled? Yeah, exactly. Let's not worry too much about magnets now. Let's concentrate on gravitational fields. So there's a lot of similarities, right? Because you know that if you're standing on the Earth, then you feel a really big pull of gravity, like it keeps you on the Earth. Whereas, you probably know that if you were hovering a few hundred miles above Earth, there would be less gravity there. That's why. It's just like with the magnet. When you're further away, you feel less of a pull. The pull of gravity is less. And also, the more massive a thing is, the stronger its gravitational field. So the sun, running out of space, but the sun is really massive. It's big. It's got a lot of particles in it. It's very difficult to move it. So it's got an even stronger gravitational field, which is why the Earth is pulled towards it and travels around it. Is that all right? So Dawn telling me that, yo, this is awesome. That's good. Right. Did I want to say anything else about that? Oh yeah. So if you've got all that, one extra word for you. The proper word for the pulling force that something made of stuff feels when it's in a gravitational field is weight. We got there. So anything made of stuff, made of mass, in a gravitational field will feel a pull towards the centre, and that pulling force that you feel is weight. So weight is a force. Weight is, like, we talk about gravity pulling us down to the ground, but really, strictly speaking, if you're made of stuff, you're in a gravitational field, and the force of gravity is pulling you down, you properly call that force your weight, right? So weight is a force. And what a force is measured in, if you've been to any previous lessons, you might remember, it's measured in newtons. One last thing before I give you some questions, and hopefully let you sort this all out in your head. Weight, you might have sussed, is different in different places, because weight is just like how you could think of it as being how much you're being pulled towards something. So Earth is pretty big, isn't it? So you weigh quite a lot on the Earth. The Moon, let's get rid of this magnet. The Moon is much smaller. The Moon is about a fifth the size of the Earth. So it's got a weaker gravitational field. And again, you probably all know that you can do moonwalks on the Moon. Like you can do huge, lovely big jumps because there's less gravity on the Moon. So you would say that you're getting pulled down onto the Moon less. So your weight, the pulling force that you're feeling pulling you towards something, is less. So you weigh less on the Moon than you do on the Earth. Okay? Mass, measured in kilograms, something totally different. Think of it as being how much stuff your body's made of. If you're made of like 50 kilograms worth of stuff on the Earth, you travel to the Moon, you're still made of 50 kilograms worth of stuff, like unless you lose an arm or something in the rocket. Mass is the same wherever you go. If a hippo charged towards you on the Earth and like knocked you over, it would do it with the same amount of force as it would do it on the Moon, okay? Things are still difficult to stop on the Earth or on the Moon. Right. Ooh. Some people struggle. Yeah, Levita's just saying, I am 9. I don't know if you're just telling me that, Levita, if you're saying, what are you talking about, woman? This is for 14-year-olds. Leave me alone. I'm going to give you some questions. And the purpose really is that the people who get it can practice with the questions, and the people who don't get it can shout at me and ask me questions until they get it. Okay, so you might have this sheet in front of you if you've got the printouts. If you haven't, then you can just either do it in your head or write it down, give you a bit of time. I've got some descriptions here. Some of them describe mass and some of them describe weight. Can you draw lines if you've got the sheet, or make some notes? Which one describes which? So what's weight measured in? Which one's a force? Which one's a measure of how easy it is to move something? There you go. And if you've finished, can you tell me which planet do you think has the strongest gravitational field? Think about your bathroom scales, or scales that you use to measure flour. What do you think those scales actually measure? Is it weight or is it mass? These are tricky, because if you've got this far, you need some tricky questions. And also, if you saw lesson 1, can you describe the forces acting on the scales? If you can think of a question to ask me, then by all means ask it. Thanks, Jack, that's kind of you. Explaining is different for different people, isn't it? I was often the kid in the class that needed explaining it 3 different ways, and the third time I'd be like, I get it. And then I do really well, but just the first 2 explanations weren't doing it for me. Right, especially physics, oh my days. Whew. The more I study physics, the more I realise I don't understand it at all. Right, let's do this then. Measured in kilograms, that is your mass. Measured in newtons, that is weight. So weight, anything measured in newtons is a force, just like anything measured in meters is a distance. If it's measured in newtons, you know it's a force, and weight is a force, okay? There we go. Different on different planets. Well, the weight is caused by a gravitational field, like a magnetic field. So bigger planets, or more massive things, have a stronger gravitational field. So weight, it can be different on other planets. I'm going to just keep talking about this, by the way, so if you don't get it now, you might later. Mass is the same wherever you go. You can think of mass as being the amount of particles in your body, and that doesn't change. You can think of mass as being how something to move, and that also doesn't change. Oh, Danielle. Oh, okay, I get it. It's just Danielle. Oh, that's cool. God, Danielle, or whoever you are, well done for sticking around. That is the biggest skill, is not getting something, but just hanging around to wait and see if you do get it. And a measure of how easy something is to move, that's mass as well. I'm more massive than my 2-year-old, because it's harder to move me off the sofa than it is to move my 2-year-old. Right. Which planet do you think has the strongest gravitational field? Well done, if you knew that the most massive planet is Jupiter. So it does have the strongest gravitational field. Oh, it's not raised, is it? Jupiter, there you go. Scales. Well, you stand on the scales, your weight pushes down on the scales, and the scales, I don't know, it's a spring or something, isn't it? Push back up. And when you stop moving, it tells you how much you weigh, actually. So scales are actually measuring weight, because they're not measuring like how hard you are to move, are they, or how many particles in your body. They're measuring the pull of like how much you're being pulled down to earth. But they talk about kilograms, don't they? It's very confusing. We get this wrong in real life all the time. The force is acting on the scales. Well, yeah, your weight pushes down on the scales. The force of the scales pushes up. And so they are balanced, right? Because in the end you don't move. That's what the scales do. They push back until you stop moving. And then they use that to measure your weight. Right. Let's do a little bit more. Come here with me. Take some more flicking. Then why is it in kilogram? Megan Marley, tell me about it. I don't know. Because most people, because like this is just one of those things that physicists say one thing, but the rest of the world, I don't know, like doesn't care, or is just getting it slightly wrong. Because that's why I said to you might want to bring along a can of beans. Hello Cora, age 8, who loves science, that's nice. Yeah, Annalise, so it's the same with this, okay? Look at this can of beans. It's telling me that the net weight of this can is 400 grams. What's that about? It's definitely wrong. There's no way this could be right. Weight is a force, is measured in newtons. And kilograms and grams measure mass. So this is definitely wrong. So this is why often physics lessons do cover the difference between mass and weight, because in real life we get it wrong all the time. I guess probably the reason that we do it is because in order to, well, I'll tell you why when I've talked about this next bit, because it'll make more sense. So we're going to put some numbers in now, because saying one gravitational field is strong and another gravitational field isn't strong and whatever, that's not really very useful. Mass and weight are very deeply connected, and you can see that with a lovely equation that Newton had a lot to do with. Your weight, how much you're pulled down to the earth, is equal to your mass times, it's an incredibly complicated long word, but the gravitational field strength. So, you know, like we talked about, the magnetic field around a magnet can be strong or it can be weak depending on if the magnet's big or if the magnet's small, or how far away you are. Everything with mass, right? Everything made of stuff has a gravitational field around it. It's a very, very weird idea. Yeah, how beautiful is that? Your weight, how much you're being pulled down to the ground, is equal to your mass times the gravitational field strength. Bear with me, all right? So let's pull the moon up again, and the earth. So on the earth, we might know that a 50 kilogram weight, a 50 kilogram mass, something with a mass of 50 kilograms, weighs more on Earth than something that's 10 kilograms. Is that okay? Something that has 50 kilogram mass is being pulled down to the Earth more than something that's 10 kilograms. Are you okay with that? Now the gravitational field strength of the Earth, as we looked at, is bigger than the moon because the Earth is bigger. So the Earth pulls you down more. The gravitational field strength of the Earth, if we want to use a number, is actually 10. We won't worry about the units for now. We'll just call it 10. And the gravitational field strength of the moon is about 2. So these numbers, I don't want to really confuse you, but these numbers are just a way of measuring how strong the pull is that you feel on the Earth or the moon. All right, so we've talked about how Earth is, to use very simple language, Earth is big, so the force of gravity is more. The moon is small, so the force of gravity is less. But if we want to put numbers on it, we'll say that like magnets, things made of stuff have this gravitational field around them, and because the Earth is big, its gravitational field is stronger. It's 10. And the moon is smaller, so its gravitational field is weaker, so it's 2. Is that all right? So to find the weight of something, you have to take the mass and times it by the gravitational field strength. So if you weigh 50 kilograms, if your mass is 50 kilograms on Earth, your weight, the force pulling you down, is 50 kilograms times 10. So your mass on Earth is 50 kilograms, but your weight on Earth is 50 times 10, which is 500 newtons. So I guess that's why the scales, even though they're measuring how much you're being pulled to Earth, I guess that's why they give it in kilograms. It's just a smaller number, because It's just a bit easier, isn't it, to read a scale and see 50 kilograms than it is to read 500 newtons. I guess that's why. I don't know. Right. I think you're ready for some questions. I think you are. I know the idea of a gravitational field is extremely weird. I think the best way to imagine it is, because we're all quite used to magnets, imagine holding a paperclip quite close to a magnet. How much do you feel a pull? If it was a bigger magnet, you'd feel more of a pull. And it's the same with stuff. You feel more of a pull if the thing is bigger. Right, there we go. So here's the question, here's the equation that I just gave you. Your weight, how much you are pulled down onto a planet, is equal to your mass in kilograms, how much stuff you're made of, if you like, times the gravitational field strength, just how strong the gravitational field is on that planet, right? So the gravitational field strength on Earth is like a medium-sized magnet. It pulls you down quite a lot, so it's 10. The Moon is like a very small magnet, so its gravitational field is only 2. Mercury and Mars have the same, 4, and then obviously the bigger planets, you feel a bigger pull, if you like, because they're like bigger magnets. Right, I'm just going to shush. Just going to try and shush myself a little bit. Oh, thanks, Ez. Thinks this is interesting. That's good. Katie's just going, ah! Oh no, Katie, I'm sorry. It's so hard not being able to see you. Do balance scales with metal weights. Oh, well done, Justine. Yeah, actually, again, that's very detailed and complicated. So no one else listened, but yes, they do measure mass, because then you're comparing a known mass with another mass. Lisa, that is excellent to hear. What is Saturn? Oh, Fran, I can't remember. I ran out of space. Ellis, hello. Oh, good. Mayo's coming up with an answer. Mayo says, is the first one 28? Well done. Hello, Noah. Oh, and EJ says 8 kilograms. All right, EJ, be very careful. Let's go through the first one. Oh, and EJ, you've got 1 mark for the second one. Right, so first of all, look at what it's asking you. This first one, how much does a cat with a mass of 2 kilograms weigh? So its mass is 2 kilograms, but weight is measured in newtons, all right? Because it's a force, it's a pulling force. So if you're looking for a weight, EJ, then your answer has got to be in newtons, not in kilograms. How much does a cat with a mass of 2 kilograms weigh on Neptune? Right, so let's have a look at this equation. The cat has a mass of 2 kilograms, and the gravitational field strength on Neptune is 14. So to find the weight of a cat on Neptune, you would do its mass, which is 2, times the gravitational field strength on Neptune, which is 14. So the answer for number 1 is 28 for 1 mark and newtons for the second mark. Well done if you got that. So EJ, can you see why your second answer just needs slightly tweaking? So EJ has said 200 kilograms for this one. Nearly right. So the elephant's got a mass of 100, but we're looking for the weight, which is measured in newtons, okay? So you got the mass of 100. The field strength on the Moon is 2, so you do 100 times 2, which is 200, but you're calculating the weight, which is a force. So it must be 200 newtons. There we go. I can go quite slowly because I think these are quite hard. Lisa wants a hug. Oh, I'm really sorry. Isn't the gravitational pull on Earth just 1? No, well, the gravitational field strength is 10. But the gravitational, you could sort of think of it as like a magnet sitting on a table, okay? The gravitational field is always there, but you don't really see it. Nothing really experiences a force until you put something near a magnet, and it's the same with this. So the gravitational field of Earth, even if there was nothing on Earth, would still be 10. But when you put something like this chocolate coin I'm going to eat in a minute near to Earth, it experiences a pulling force, just like a paperclip does with a magnet. And that pulling force depends on how much the chocolate coin, how much its mass is, all right? So if it weighed like 10 kilograms, it'd be pulled down less than if it weighed 100 kilograms. It'd be pulled down a lot. But the gravitational field strength is 10. Is that right? How did they find the gravitational pull number for each planet? Sally, what a brilliant question. No idea. Hiya, Ruben. Right, let's go on then. Question 4. Karis says still 40. Right, let's go. A dog's weight on Earth is 10 newtons. How much does it weigh on Jupiter? Okay, so now we've got the weight. So we know that this is 10, okay, for the dog. And its weight on Earth is 10 newtons. So what do we know about the Earth? It's got a gravitational field strength of 10. So for question 3, we know that this number is 10, and we know that this number is 10. So 10 equals something times 10. 10 equals something times 10. Well, 1 times 10 is 10. So that the mass of the dog must be 1, all right? Because the dog weighs 10 newtons. So 10 newtons equals 1 kilogram times 10. So if the dog's mass is 1 kilogram, then you've got to think, okay, it's on Jupiter now, where the field strength is 25. So its weight would be, it's 1 kilogram times 25, which is 25. And what's the unit? Are we looking for mass or weight? Oh, we're looking for weight. So again, 25 newtons for 2 marks. Yeah, well done. Number 4. Your mass on Mars is 40 kilograms. What's your mass on Jupiter? Mass never changes. If you've got 40 kilograms worth of stuff in you, or if you're 40 kilograms worth hard to move, then you always are, wherever you go. It's not affected by the gravitational field strength of anywhere. Well done if you got that. Could you jump higher on Mars than on the moon? Just scrolling through comments. Ah, you can't do the last one. Good, Layla. I'm glad. I was hoping people would get a bit stuck on the last one. The last one's tricky because I was putting it there to fox the people who are going fast. Skimming through. Okay. Could you jump higher on Mars or on the moon? Well, Mars is pulling you down twice as much actually as on the moon. So you could definitely jump higher on the moon. You could jump twice as high on the moon as you could on Mars because you're getting pulled half as much, only 2 instead of 4. And this was a horrible trick question to fox you people because you were going too fast. Your weight on Earth is 40 newtons. How much more massive are you on Saturn? Well, it's a trick question because how massive you are doesn't change. If you're 20 kilograms, you're 20 kilograms wherever you go. So I don't know how you would write that in words. Not any much more. If it was GCSE, I'd probably write, mass does not change. But you see what I mean. Right, you lot. Now, I think it's working nicely that... Wait, where are you? Hello. I think it's working really nicely that we put in a natural break for the people who are maybe younger or haven't done as much science. So if you're under 14, because this is all GCSE stuff, or if you haven't done that much science before and you're thinking that your brain has had as much exercise as it could possibly take, I think you should leave the lesson there and give yourself an enormous pat on the back. Shall I read you what you actually need? For Key Stage 2, the information that they say you need is the force that pulls things to the ground on Earth is called gravity, and gravity holds the Earth and the other planets around the Sun. There's gravity on the Moon, but not as much as Earth, because the Moon is smaller. So if you know that now, Moon, small, less gravity, then well done. You passed your Key Stage 2 exams. And then Key Stage 3, all they do is they also say that if you're closer to something, you feel a stronger gravitational pull. Gravity is stronger if you're close to something than it is if you're far away. But thank you so much for coming, everybody. There's a couple of new people here, so I will do my little ad. And then, usually we do a GCSE question at the end, don't we, for people who just want to see, just out of interest, and like have some fun doing some tricky stuff. Because this is all GCSE content, I've got an A-level question. But it's worth 3 marks. We'll see if you can get a mark. But anyway, yes, my name is Lara. Hello. I'm running this science communication business called Theatre of Science. I've been doing free shows every week since lockdown started. And now I do this home ed lesson as well. So the weekend show is at 10 o'clock, Saturday and Sunday. It's the same show both times. And that's a bit more entertaining and a bit lighter. You bring stuff, you do activities. I tell you a Lego story time. And it's a bit more just you going, oh, cool, and me doing all the work. This is definitely the tricky one, isn't it? Where you do all the work. Hello, Alina. In year 4, fantastic. Yeah, if you really liked this, I just got 20,000 likes on Facebook. So I don't need you, but I do. Please, could you go to my Facebook page and press like? It makes me so happy. You like my Facebook page? You could share this with other people that you know who are home editing. That would be super cool. Thank you very much. You go to my YouTube channel and subscribe if you want. Or if you really love this and you want to support me and you're going to come all the time, and I have got a website called Patreon that's for podcasts and stuff, where you can support me with £3 or £5 or £10 a month. For £3, I send you these rainbow glasses, Amazing Rainbows, and I send you a thing explaining how they work. And for £5 a month, I send you this bi-monthly magazine. It comes out every 2 months. It's out very soon. It's going to the printers this week. It's on snow this time, so I write it. My graphic designer husband makes it look very pretty. And the idea is that it's kind of like the shows, but on paper. So there's some stuff that for 6-year-olds and some stuff that like 40-year-olds won't have a clue about. So hopefully it fits all ages. Right, hello Emma in year 5. Okay, I think that's my ad over. Brilliant, let's do it. Oh, okay, so anyone's still here? I'm assuming you want to see this A-level question, okay? You do really have to have been to the other lessons to really understand it. But I'm going to give it to you properly, actually. Come down here, I'm going to give it to you properly because it's 3 marks. Thanks, Brooklyn. That's very nice of you to say so. Well, thank you for sticking around. You've all done incredibly well today, I can't tell you. Here we go. Check this out, right? A-level. So those of you who don't know, A-levels are the exams that you take when you're 18. You've learned so much physics by the time you're 18. You take these A-levels, and here's one of the questions. So the only things I've done are I've changed the numbers because the numbers were very hard and complicated and you'd need a calculator. But apart from changing the numbers so that we can sort of see more easily what's happening, this is exactly what they got at A-level. The Saturn V rocket used in NASA's space program had a mass of 3 kilograms. Obviously, it was more than that. I've changed it. It took off vertically, so vertically means upwards, but you probably guessed that because it's a rocket. With a thrust force, someone said thrust in our octopus lesson the other day, well done. Thrust just means like pushing forward. So the thrust force is pushing it forward with 40 newtons. Show that the resultant force, we did that last week, the overall force on the rocket is about 10 newtons. This isn't cheating. I think you'd have this equation in the exam, or you would have done when I was teaching A-level. So weight equals mass times gravitational field strength. Have a go. Have a go at that. It's worth 3 marks. So think about the things that you might need to do to get 1 mark. Stephen, you are so welcome. Thanks, David. Oh, thanks, Sadaf. Hi, Alice. Age 9. Isn't that amazing? Alice, are you still here? It's so incredible that I'm showing you an A-level question, but I think it's fine, you know? It's only like sort of taking ballet classes, isn't it? And watching a professional ballet. You don't watch a professional ballet and go, oh no, this is terrifying, I'm never going to be able to do that. You're just like, oh, interesting. Wow, oh, Kim, hello. Hello, Marley, age 8. Oh, bam. Marley, well done. That was fast, dude. I can't even read that number, Gareth, but thank you. I am going to aim for that many Facebook likes. Kim, nice. Meg, it would be different if it took off from a different planet. Well done. Right, shall we have a look? First of all, maybe after today's lesson, you could see that if we're talking about forces and we want to know what the overall force is on the rocket, knowing that its mass is 3 kilograms, that's not very useful. We're going to have to change this into a force so that we're working in forces, right? How do you change a mass into a force? Well, weight is a force, so let's work out the weight of the rocket. You do its mass times the gravitational field strength of the Earth, because it's on Earth, so that's 10. So you do 3 kilograms times 10, which is 30 newtons. Well done, you would get a mark for that at A-level. And then you needed to know about resultant forces. So I've drawn the rocket to help me. It's a thrusting force pushing upwards of 40 newtons. But now we know that pulling down on the rocket is the rocket's weight, pulling it back down to Earth, which is 30 newtons. And yeah, if you came last week, you might remember that the overall force acting on the rocket is forces in opposite directions. They cancel out. So if you've got 30 pulling down, that would cancel out 30 pushing up. And like a few people have said, what you're left with is 10 newtons overall acting upwards on the rocket. So you got 1 mark. You got 1 mark for knowing that to get the resultant force you needed to do that, and you got a mark for the correct answer as well. Now the correct answer would have had some like decimal places in it, but we're not worrying about the maths, we're worrying about the understanding. So very well done if you got that. Oh, Toby enjoyed that, that's good. One last thing for you. Rosie, age 7 just got it. Rosie, isn't that brilliant? You're 7. Well done. It's about having the confidence, isn't it, to try these things and look and think and not just go, oh, can't do it. Chloe, age 9, well done. If you didn't get it and you're still here, congratulations. Give yourself a massive pat on the back. If you have got a strong enough mind to be able to look at something you don't understand and just go, yes, I don't know, I'll find out the answer later. That's amazing. That is so amazing, and that skill will get you through. People do not fail their GCSEs because they try their hardest. People fail their GCSEs because they just go, can't do it, skip that one, boom, I'll just sleep on the desk for half an hour. So very well done. Well done, Lewis. River, age 11, that's a perfect way of putting it, River. Understood an A-level question. Exactly. Doesn't matter if you didn't get it. It matters if you've understood it, you're thinking about it. Right, I'm going to stop. I'm just so proud of you guys. I'm going to stop blabbering on, but I will show you this that we looked at lesson 1 to just show you the thinking behind GCSE questions, because they're evil. Do you remember this from lesson 1? 2, the diagram shows a skydiver in free fall. He's got 2 forces acting on it. X is pushing up on the skydiver and Y is pulling down, and they wanted you to complete this sentence. You had to cross out the 2 that were wrong. They were basically saying, what is force X? What force is pushing up on the skydiver? Is it friction, is it gravity, or is it weight? Oh, can you see now what they were trying to do? Quite a lot of GCSE students, when they read that question, went, they're trying to trick me, but I know that it's not gravity, that the proper answer, the proper word for a force that pulls down on someone is weight, so they ticked weight, whereas obviously it's not either of those things. Y is the weight pulling the skydiver down, but X is pushing up, so it must be the force of like air resistance, which is a kind of friction. But there you go. So that was, I just thought that was quite interesting. That's how they're testing you. Okay. Right, you lot. I'm exhausted just watching you try that A-level question. Very well done. If you have made it this far, I am so impressed. I'm very excited to be teaching you incredibly resilient, brave people more physics. So what was it next week? Is it turning forces or balancing forces? I think it's turning forces. I think I'm going to show you. You guys know that I love Jurassic Park. I think I'm going to show you the only bit of Jurassic Park next week that really, really annoys me because some of the physics in it is wrong. Oh, did you notice anything weird though, actually, that I was going to tell you because you guys are very interested? Did you notice that Mercury and Mars have the same gravitational field strength? Did you see that? What's that about? Because Mercury's a lot smaller than Mars. Look, you can see, I did it properly. Mercury small, Mars big. Same gravitational field strength. Why? It's because they are made of about the same amount, they've got about the same amount of stuff in them, but Mercury is a lot more dense. So if you got Mars, squished it, you'd get Mercury, kind of. And gravity is caused by mass. So although Mars is bigger than Mercury, weirdly they've both got the same mass. We'd say they have different density. Same amount of stuff, but on Mercury it's closer together. There you go, a little extra bonus for you who are still here. Thanks, Julia. Exactly, yes. John,